All right, so we showed a few of the distributivity properties of of not, and of how when proving stuff like this number 8, if you're stuck without any arguments, usually that means you need a lambda somewhere, and you should try introducing a lambda to get some arguments. And now I wanted to skip ahead a little bit just to get to something slightly more fun. I recommend you try a lot of these on your own before watching videos about them. But we're actually going to get to an interesting one here at the end. P implies Q implies not Q implies not P. And this is the contrapositive. But this is actually the contrapositive in one direction, right? So if you notice, a lot of these are if and only ifs, right? But interestingly enough, this is, if you might recall from classical logic, this is true if and only if not Q implies not P. I mean, it's true both ways. That it's interesting and not a coincidence that this goes one way. And that's because to prove it in the opposite way, you actually need decidable logic, as far as I can tell. Because I don't think there's any way of getting rid of the nots when you prove it the opposite direction without using a proof by contradiction. But you're welcome to try and prove me wrong on that. So we're going to prove it to the right. And we're going to prove it in tactic mode first, and then I'm going to show you a beautiful proof in term mode that is really quite surprising. So in tactic mode, we know that we need to introduce immediately an argument, right? We have an implication in the goal. That means we use intro. Intro HPQ to introduce our function P to Q. And now we need to show another function, not Q to not P. So if we need to show a function in the goal, that means we need to use a lambda. But actually, we're in tactic mode. So instead of using a lambda in the goal to show the goal, we're going to just intro again to get rid of that implication, right? H not Q. And now I just need to show not P. And this is, we can do this double intro here because not Q to not P has parentheses around it in the problem. But they're actually implied parentheses. The only parentheses that matter are the ones around P to Q, which enforce that this first argument is one argument and not two arguments, because if we took those away, it would be two arguments. But much like Haskell, Lean uses the same kind of associativity here. So Lean says that we're going to group our parentheses, make sure that I get this right. We're going to group expressions to the right, right? So if you have something like, let's just get rid of these for a second here. If you have an expression like this in Lean, this is implied that it's actually one function. And that's a little bit weird, but it's because of currying. This is actually one function from P to another function, which is one function, takes one argument, from Q to a function that takes one argument, etc., etc. And so that's why we need those parentheses up here, but also why these parentheses are actually implied. And when you take away those parentheses, it becomes clear why we get to do this double intro. Okay, I'm going to leave them up there, though, because I want to prove exactly what the book had as a goal. And for intro HPQ, intro HPQ HNQ, gives us a function from P to Q and a function from Q to false. We need to show a function from P to false. And so suddenly we notice that there's another implication in the goal, which is strange. But there is, because this is a not P. So we can actually say HP and introduce a third hypothesis. And that leaves our goal as proving false. And that's because to prove not P, you need to assume P and show false. Okay, well now it should be clear we have all the ingredients, right? We just need to cook. We have HPQ to map P to Q, and then we have not Q to take Q and turn it into false. So this is just function application. We're in tactic mode, so we're going to use the apply tactic. Apply takes a hypothesis and an expression and tries to apply the hypothesis to the expression. So if we're here, we have P and a function from P to Q. Clearly we need to apply HPQ to HP. Okay. And we're getting an error message here because apply is trying to unify the result of this with the goal. And the goal of false is clearly not what you get when you apply HPQ to HP. What we can do, I think there's a tactic, I think we can use replace to do what we're trying to do here. Let's see if that works. Replace is going to try to take a hypothesis and update it with some new information, basically, according to what you give it. So we're going to say replace HPQ with the results of HPQ to HP. And, but that, it gets us closer to the goal, but this isn't really the right tactic to use, right? Because clearly HPQ shouldn't be messed with. We'll just start building it up with exact, right? Because we know that it's just a sum. You know, that's not right. We can introduce new hypotheses. There's no reason we should shy away from that. So we'll say after HPQ HP, we'll just make a new hypothesis. We have HQ, right, by HPQ to HP. And we have false from applying HNQ to HQ. So we can say apply HNQ to HQ, and that works, but better practice is to use exact, because exact closes the goal completely. Okay, so we've proven the contrapositive. That wasn't so bad. Most of the work was done by recognizing that intro can actually take 3 arguments here, which is a little bit surprising, given that it looks like this function only takes 1. Now it's time for the far more flashy proof. So this is tactic mode, but we're going to prove this in exact mode. And the proof is actually going to look like a face, which is really cute. So we'll do it one way, and then we'll simplify it down to the face expression, which I love. Okay, so we'll just take the same approach that we did in the tactic mode at first. We're going to intro HPQ with a lambda. And now we need to give back, after that, we need to give back what? We need to give back a not Q to not P. And so we can just introduce, instead of making a new lambda, Lean will do this for us. Lean will do the currying for us. So we can always just have a lambda with multiple arguments. We can introduce the other arguments, HNQ and HP. Okay, so clearly we could do what we did in tactic mode, but a bit more concisely, right? We don't need the intermediate steps. We can just say HPQ, HP, surround those in parentheses to get HQ, and apply HNQ to that to get the result. Okay, well that's not a face yet though. How do we get the face? All right, well, what we can notice here is that the arguments that are declared line up very nicely with how they're used, right? this function is almost just taking arguments and applying them in the exact same way, which is just a more complicated way of doing ID, right? In this case, since there's parentheses around the HPQ, that means that this is actually doing function composition, right? Because we're applying HPQ to HP, and then we're applying to HNQ to HPQ. So let's rewrite this in terms of function composition. In Lean, function composition can be written with the following sequence of characters, \comp. And that gives us our function composition. Now I copied this wrong because this is HNQ after HPQ. And this builds a new function that first applies HPQ, then applies HNQ. Okay, but now we're going to do a little bit of currying here because we don't actually need the HP as an argument if we curry it out. And that's kind of just like stating ID in functional programming language, right? If you have ID, and you can prove this by, giving a lambda from HP to HP. Let's say PQ maybe something a little bit more complicated. We can do this by, HP, HQ, HP, HQ. Whoops, let's make sure this works. No. That does not work. Okay, bad example. What I'm trying to illustrate here is that if we take a function from P to Q, and we take an argument of P to show Q, then that's basically the same as saying just return the function, right? Because if we go through the trouble of applying HP to HQ to get Q, that's basically doing this, taking this as an argument, taking this as an argument, and proving this. But we don't have to do that. We can just take this as an argument and give it directly back as a proof, right? Because it matches. So we can just take away the HQ here, and that works just as well. And we don't even need to use our own lambda because this is already defined as ID, right? This is ID specialized to a function from P to Q. Okay, well, how can we apply that down here? We can apply that down here because what you might notice is that composition here is working on both arguments in order, which means that really this lambda is just function composition. It's just \comp on its own, but rewritten with more arguments. And we don't need those arguments. I mean, they don't look very nice. They don't look like a face, right? So we can get rid of the lambda, and we can just give comp two implicit arguments, and \dot is for making a lambda. I believe it's called section syntax in Haskell, something pretty similar to that, out of an operator. So this is an operator, and we're trying to make a function from it without applying all of its arguments. In this case, both arguments, the left and right side, are not being applied. Okay, now we get a bit of a tricky error because it seemed like this should work. It seemed like, taking the composition of two arguments in order should be just composition. But it's actually, we actually flipped the arguments. Let's see if we can deduce why. Oh, yeah, no, they're just flipped in order. I didn't even notice. So HPQ actually is over on the right side instead of on the left side. So that means that we know, let's go back here. That means that we know why this isn't working. Now we need to flip the arguments. And now we get our face proof, right? So this is a proof of the contrapositive using simply a slightly different order of function composition. And again, this goes back to the Curry-Howard isomorphism. This is a beautiful example of two seemingly unrelated ideas. One in logic that says, you know, if P then Q, well then not Q implies not P. And one from functional programming, which says that these functions, two functions, can be hooked together to make one function from the first input to the second's output. And to see why this is the case, like usual, we can just replace all of the nots with their definitions, right? So not's defined as a function from P to false and a function from Q to false. And then we'll need to remove some of these parentheses to see this a bit more clearly. We said that the implied parentheses, there were implied parentheses around the second two arguments because Lean groups things to the right. And these are not implied parentheses. We can't get rid of those. But now this should be more, this should immediately be clear. We are proving that from P implies Q and a function Q implies false, that we can skip the Q and show false directly from P. And that's function composition, right? And if we wanted to, we could just change the order of the arguments because it doesn't, you know, it doesn't change the validity of the proof. We know that P implies Q implies R is the same, well, it's equivalent to Q implies P implies R. Just the ordering of the arguments is different. And this version wouldn't need a flip, right? So this would just be basically the same proof, but without the flip.